Now let's talk about the application of the OSI model into the network architecture. Your local area network is almost always implemented using switched Ethernet that we use a copper twisted pair cabling. We also use wireless communications, and that's becoming more and more popular to connect us in the local area network. Now, as local area network grows and traffic increases, it's going to be important for us to look at some sort of logical configuration and find methods to be able to optimize that traffic. That also means we might move into a different layer. Now, the switching layer, as I'm going to diagram out for you, is in layer 2. We can find ways to help separate a lot of this traffic by going to layer 3 of the OSI. And I'll demonstrate that for you as I talk a little bit more about that interrelationship. Now, in the design of your local area network, you have to take into account the cost, speed, flexibility, and reliability. That means we want to look at the type of media we're going to use to transmit the data. We want to talk about the type of physical network mediums that we're using. We also have to have an understanding of the performance and security regarding how data is going to be transmitted across that network. The physical media that we use to connect various hosts of these computing devices are things like copper cables. And in that we use what's called twisted pair. Now, it gets that name because it has 4 sets of 2 wires, pairs, that are and the 2 wires are twisted around each other. It's done in a way to be able to protect from an issue called crosstalk, where a signal could jump from one wire to another wire. Anyway, so we've got the twisted pairs. Now, your copper cable doesn't get to run very long. Believe it or not, even though you're sending electrons down this copper wire, and they're going to go, really fast, not quite the speed of light, but as they're going down, they're going to get tired because, there's still energy being used to go down that copper wire, right? It's just like you running a race. You might start off strong, but you're going to start to kind of wear out at the end. And so there's a limit to the length. And that length is that limit is called the attenuation. When the signal gets weaker and weaker and weaker to the point that it's no longer really something we can use. Most often that's about 100 meters in most of the copper solutions. Now, fiber optics give us high capacity. And we have some options there. I'm not going to get into the single mode, multi-mode types of fibers. I'm not going to get into a discussion about all the different types of optics. But let me just say that you can have some fiber optic runs that can be, a couple hundred meters. You can have some that are in the hundreds of kilometers. One connection all the way through. And really, think about it this way. We have fiber optic connectivity between the United States, Europe, Japan, Australia, Alaska, which is part of the U.S., I know, but we still go around Canada to get there, Hawaii. And this cable is underwater. It's in the ocean, and it's connecting us from one end to the other. So, we can get a lot of runs. Now, don't get me wrong. They do have to have repeaters because I don't think they yet have an optic strong enough to go the 5,000 miles across the Pacific. But, it goes a long ways. We also have infrared and radio frequency. Now, I could mention in there satellite, but that's not really a big local area network connection that we have. But I've seen that solution used for a local area network at a location, a college football arena to be specific. But anyway, those are options that we have. And you know what? They're all about sending ones and zeros. It's just twisted pair copper does it with electrons. Fiber optic is sending photons, light, down to the that little glass tube as it goes all the way through. And infrared and radio are using different types of frequencies to be able to send this information. Now on the wide area networks, we're almost always going to be seeing fiber optics here. It's very common for use because they're high capacity, and we're talking about high capacity network connections. And there might be, even if it's not in the wide area network, you might be using it what we call a campus area network, one of the ones I didn't mention, where you're connecting between buildings on the same, general grounds. So it can be between cities. It can be other types of long hauls, like I just described with the oceans. Now, besides that, like I said, you do have satellite radio links. You also can use microwave radio systems. The only problem with microwave is it is line of sight, and it's not that high a speed compared to what I can get out of fiber. And certainly satellite isn't either. fact, satellite is one of those things I'd use at like the last resort because it's the latency on it is just horrible, and the speeds and the rest. But anyway, I'm digressing. There's other systems though. Those can also be part of the wide area network. Well, in the LAN, local area network, your common media access technology is Ethernet. It can be copper, it can be fiber, but it's Ethernet. We used to use token ring a lot. I'm just going to tell you, there used to be token ring. That's all I'm going to tell you about it. Now we've got Ethernet. So Ethernet began as a bus configuration. It used a 10 megabit capability of speed, and it did it over a coax cable, short for coaxial. If you've got cable TV, you know what I'm talking about. From that bus design, it went to a star configuration, initially using hubs. Again, it was using the copper twisted pairs for the cabling. Now, you don't need to know all about the different categories of copper cabling, but if you care, you can look up category 3, 5, and 7, or 5E and 7. We use those a lot. 5E is capable of getting up to that gigabit speed. We'll look at that. But anyway, the cabling, the speed has improved. The initial IEEE specification for Ethernet was under 802.3. And then we saw revised specifications to get to a faster speed, which we called fast Ethernet. Then we got faster, and we got to gigabit Ethernet, which was 1,000 megabits per second. The fastest was 100 megabits per second. We surpassed that, and we got into 10 gigabit Ethernet. And yes, we are now at 100 gigabit Ethernet. We also have a 40 gigabit Ethernet capable system as well. That is a tremendous amount of bandwidth increase over what we had 10, 15 years ago. And it's growing fast. The time, it seems to me, and I don't know this factually, but it seemed like to me that it took us forever to get from fast Ethernet to gigabit. And then it wasn't so bad getting to 10 gig. And like, as soon as I got comfortable with that idea, we were talking 100 gigs. And I'm just like, what's next, right? Terabits. Okay, well, not yet. On the horizon, I'm sure. Now, Ethernet uses what's called carrier sense multiple access collision detection. I'm going to try to illustrate that as I talk about some of these different types of network devices at the same time. So you're going to see me come back and talk a little more about Ethernet, about this CSMA, carrier sense multi-access collision detection, along with a lot of these other concepts. I'm going to kind of try to wrap it all up for you in another illustration.